Mr. Mount here. Hope everyone's doing well at home. I wanted to take a few moments here to review some basic aspects of light, also known as electromagnetic radiation. Okay. In the previous lesson, you looked at a few videos which talk about light and specifically how light is used in exploration. Those were NASA-produced videos, and I want to take a few moments just to review some basic characteristics. Okay. In this, the slides you're looking at here, I've also shared with you in Google Classroom. Okay, so light is also called electromagnetic radiation. Okay, these are different types of light in this diagram. Okay, we start with things like radio waves, and we go from there down to microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. Okay. Now, light has wave-like characteristics, meaning that light, much like ocean waves, light comes as a wave. Okay. Things like radio waves, AM, FM, etc., Wi-Fi even, have larger wavelengths, meaning the wave is larger. Okay. Sorry, the wave is larger. AM radio, that's staticky radio your parents might listen to or your grandparents. The wavelengths of AM radio may be the size of buildings or even small mountains. Okay? FM radio that you're probably familiar with, the wavelength may be several meters in length. Like a typical FM radio wave may be 2 or 3 meters. On the other hand, some types of light have very small wavelengths. Visible light is about the size of a living cell. When you get down to ultraviolet and X-ray, their wavelengths are literally the size of a molecule or atom. Okay? Now, some relationships you should understand. Larger wavelengths have less energy and are less frequent. Okay? Smaller wavelengths have more energy and are more frequent. Okay? Frequency is how many waves you get in 1 second. Okay? And energy is just how much energy the light carries. Okay? So these larger wavelengths like radio and microwave don't carry as much energy. Okay? Because they have longer wavelengths. When we get down to these things, these can do a lot of damage because they have a lot of energy. Ultraviolet light, for instance, causes sunburn and can mutate your DNA because the waves are so small, it carries more energy. Some other things about light. Okay, light carries energy. All light moves at the same speed. The speed of light, 300 million meters in 1 second. Okay. Now, another thing about light is like a wave. It's also like a particle, okay? As I said a few moments ago, much like ocean waves, light has wave-like characteristics, okay? Meaning that you have a wavelength, the distance between the same point on two waves that are next to each other. The speed of all light is the same, 300 million meters per second. And frequency, how many wavelengths or complete waves pass a given point in 1 second. Okay? So in these ways, light is like a wave. Light is also like a particle. Okay? And this was discovered about 100 years ago by this guy, de Broglie. He's a French guy. Light is like a particle. We know that because light interacts with matter. Okay? Again, think about sitting in the sun. Eventually you get warm. Why? Sunlight is interacting with your skin. Okay? So light is like a wave. It's also like a particle. Okay? Some other things. This section here, there's a connection between light and electrons. Okay? Our understanding of how electrons are set up in the atom comes from analyzing light given off by an atom. Okay? And that's what you really need to know here. Okay? These guys, Bohr and Schrödinger, came up with the model of the atom that we've done in class, where you have the nucleus in the middle surrounded by rings of electrons. We know that because of the light that atoms give off when they get energized. Okay? So light tells us about electrons in the atom. The relevant light that's analyzed for that is visible light, infrared, and ultraviolet. Okay? So when you energize atoms, the electrons in those atoms can give off either infrared, visible light, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, or ultraviolet. And that tells us about where the electrons are in an atom. Okay? You may remember the flame test lab from earlier in the year, where you put a drop of a solution in a Bunsen burner, and depending on what element was in that solution, it gave off a certain color of light. Okay? If you were to look at those flames with a spectroscope, which is a fancy kind of prism, and you'll see that a little later in the video, each element gives off specific lines of color. So for instance, hydrogen gives off this line, and these two lines of color. Okay? Those specific visible wavelengths, visible colors, tell you about the electrons in hydrogen, and these are unique to hydrogen. Okay? Here's mercury. You have some lines here, a couple here, some right here. Okay? Here's neon, where you have a bunch of lines in the orange and red, some green. Okay? Here's one more. Argon, you also have a number of lines, a lot of reds there, greens, blues, and violets. Okay? So each element, depending on its electrons, gives off its own pattern of specific wavelengths. Okay? We call that an emission spectra. Coming back to this for a minute. So these are the relevant wavelengths of light when we analyze the atom: infrared, visible, and ultraviolet. Okay? Now, a couple last things here. Light relationships. Frequency and wavelength have an inverse or indirect relationship. You may remember those terms from the gas laws. And what that means is, if you have a big wavelength, you have a low frequency. Bigger waves are less frequent. If you have a tiny little wavelength, that light is going to be more frequent. Okay? I'm not going to ask you now to use the equation, but just understand the relationship between frequency and wavelength. It's indirect. The energy in light, energy and frequency, there's a direct relationship. Okay? If light waves are more frequent, they transfer more energy to matter. Radio waves won't really do much to your body because the waves are so big, they're not very frequent, and they carry low energy. Whereas again, gamma rays would do a lot of damage to you. Gamma rays are extremely frequent and carry a tremendous amount of energy. Okay? So if light is less frequent, it carries less energy. If light is more frequent, it carries more energy. Okay? Now, in the next part of the video, you're going to look at a demonstration which talks about light absorption and reflection. Okay? Chemical substances will absorb some colors of light and reflect or transmit others. And we can actually use that to identify a substance. Okay? So look at this in the next part of the video.